We are going to discuss certain materials called shape memory alloys that can remember their shape. The specific nature of the shape memory alloys is due to the inherent behavior of the materials. Shape memory alloys are used for diverse fields of application for their superior thermomechanical properties. The most common used shape memory alloys are copper, zinc, aluminum, and copper. Uncoiled spring coils back and returns to its original shape when it is placed in hot water. Well, this happens because the wire is made of Nitinol, which is a shape memory alloy, upon cooling. This behavior of the shape memory alloys happens due to the change in crystalline structure, and to understand what exactly happens when SMA is heated, we need to know some more basics. Austenite is a crystalline structure that exists at high temperature and it cannot be easily deformed. It has a definite, fixed, long-range arrangement of atoms in the material. Whereas martensite is a soft, crystalline structure that exists at low temperatures and it can be easily deformed. The deformed martensite will remain deformed unless it is heated. That is, when a martensite is heated at high temperature, the internal stresses developed due to the heat supplied in turn changes the crystalline structure of the martensite into well-ordered austenite. Similarly, the austenite phase returns to martensite when it is cooled. This is a solid phase transformation process. Solid phase transformations, there will be a change in the molecular arrangement, but the position of atoms remains unchanged with respect to its neighboring atoms. In simple words, the transition looks like stretching a square into a rhombus or a rectangle into a parallelogram and vice versa. Now, let us point the transition stages in a graph. The temperature at which the transition from martensite to austenite starts is noted as AS, and the temperature at which the transition finishes is noted as AF. Similarly, the starting and finishing transition from austenite to martensite are noted as MS and MF. This transformation exhibited by the shape memory alloys because of the applied temperature is known as shape memory effect. As said, martensite can be easily deformed when a force is applied and stays in the deformed shape even after the removal of the force. Thus, martensite can exist in more than one form. But when heated, any form of martensite can transform into austenite, and upon cooling, they return back to the original shape before deformation. In addition to shape memory effect, shape memory alloys have another specific feature called pseudo-elasticity. We come across several elastic materials in our day-to-day life. Elasticity is the property by which the material regains its original form upon removal of the applied force. But pseudo-elasticity is the property which occurs due to the change in crystalline structure. Assume that we have a shape memory alloy which is at a high temperature. At this time, the material will be in austenite state. When a force is applied, the material deforms into martensite and returns to austenite when the force is.
Next one is the temperature-induced transformation. The phase transformation takes place in a shape memory alloys over a range of temperature. It is not occurs at a particular temperature. It is the over range. This is called the temperature-induced transformation. We will take it now the temperature along the x component, x-axis. Along the y-axis, in the left-hand side, I take it now the fraction of martensite, and right-hand side is the fraction of austenite. Already we know about the martensite. Martensite is the low temperature phase. So you take it now the low temperature, this is higher temperature range. At low temperature range, it is exhibits the martensite. It is continue up to a certain limit. Suppose I increase the temperature value, it is changed to the martensite. So the martensite is changed to the austenite between these 2 points. After this point, it is exhibits the complete austenite materials. So this point is called at now austenite starting point, and this is the austenite final point. Between these 2 points, the part of the material have the martensite and remaining part of the material exhibits the austenite properties. Suppose a cooling effect is increased, I apply the cooling effect. So the austenite is continue up to a certain limit. After this point, it is changed to the molten site. So this is the cooling effect. So this point is moltenite starting point and this is the moltenite final point. Between these 2 points, the both stable states or exhibits, or both phases or exhibits. So some material exhibits the austenite phase and some material or exhibits the molten site phases. So this is the complete graphical representation for the temperature induced transformation of austenite and molten site. So this point is the pure austenite material. So the molten fraction equal to 0. This is complete molten site material, so its value equal to 1, fraction value equal to 1. The right hand side, here this is the complete molten site, so austenite ratio equal to 0, fraction equal to 0. This is the complete austenite, so the austenite fraction equal to 1. So next one is the shape memory effect. The recovery of strains imparted to the material at low temperature as a result of heating is called the shape memory effect. This line is represent the temperature value and this line represented the load value. This is the lower temperature and this is the higher temperature value. Already we know the high temperature materials or austenite and lower temperature materials is the phase is the molten site. This is called twinned molten site. So the austenite material is involved in the cooling process. Its phase transformed to molten site, twinned molten site. So after change the twinned molten site, you apply the heating effect. It is converted into its original shape or austenite shape. So this is the two-way shape memory effect. Suppose the twinned molten site is under the stress or any under the load value, it is changed to deformed twinned molten site. This is the deformed shape. So this transformation occurs only depend on the load or stress value. The deformed twinned molten site material involved in the heating process, it is returned back to the austenite shape or austenite materials. So this is the one-way process. So without any load, you apply the cooling effect, the austenite material is not gain it deformed twinned molten site shape. So this is the one-way shape memory effect. Pseudo-elasticity. The formation of stress-induced molten site from austenite phase result in a phenomena called pseudo-elasticity. In this case, this is the temperature line, this is the load line. In general, higher temperature is austenite phase, lower temperature is the molten site phase. But here, the deformed twinned molten site phase is occurs at a higher temperature range. So this deformation is occurs only depend on the stress value. At higher temperature, the austenite material under the stress value, it is converted into deformed twinned molten site. Suppose if you remove the stress value or load value, it is regained its initial austenite shape. This transformation is occurs at a higher temperature. So due to the stress or load value, without the temperature change, the deformation is called as pseudo-elasticity. Nickel titanium alloy or Nitinol. The Nitinol stands for Nickel Titanium Novel Ordnance Laboratory. The nickel alloys exhibits two closely related and unique properties. One is shape memory effect and another one is pseudo-elastic effect. The shape memory effect is completely dependent on the temperature value and the pseudo-elastic effect is completely dependent on the load or stress value. It is temperature induced process. This one is the stress or load induced process. It exhibits the enormous elasticity, nearly 10 to 30 times that of the ordinary materials. Nickel titanium alloy or Nitinol properties. It have high melting point around 1300 degrees Celsius. The transformation temperature ranges 200 to 110 degrees Celsius. The
Nitinol. Nitinol is an alloy of nickel and titanium in proportions of 45% titanium and 55% nickel. This alloy has a unique property that was discovered in 1961 by American scientists. The property of this alloy is called shape memory. So, to demonstrate this property, let's conduct an experiment. Take a clip of Nitinol and deform it. Besides the clip, I as well have a spring made of Nitinol, which I also deform into a random shape. The activation temperature of Nitinol is about 40 degrees Celsius. I have turned on the burner on the stove and put the deformed Nitinol clip on its surface. Over time, while heated, the clip begins to return to its original shape. The same thing happens with the spring. This happens because when the temperature changes, the crystal lattice configuration of Nitinol changes from one phase to another. Also, Nitinol is 10 times more elastic than other metals. While Nitinol restores the shape, it can also do some work. Let's see what kind of work a small spring of Nitinol can make. I have attached the spring to a tripod and hung a porcelain basket onto it, which weighs 180 grams. Next, we stretch the spring. For the spring to be tightened again, I'll heat it with a lighter. Let's proceed. As you can see, the spring has left the basket quite easily. Now we'll complicate the task. I'm adding metal bears into the basket, and the total weight now becomes 278 grams. Testing the spring. As you can see, the spring can easily handle that task. Adding more weight. I now put the stone and a piece of pyrite into the basket. Total weight is now 414 grams. And as you can see, nothing can stop the power of our spring. In order to ensure how big is the power that Nitinol creates when restoring the form, I hung a YouTube silver button on a spring, which weighs about 1 kilogram. Trying again with heating the Nitinol, and what we see is even this huge weight can be risen by the spring very easily. However, you could now probably ask, if it's
Application of shape memory alloys. The shape memory alloy used as the tensile arch wire. This is the tensile arch wire. It will make the misaligned teeth gradually to original shape. So next one is the SMA used as the blood clot filter and also the stent in the coronary artery block. So this is the cholesterol is occupied inside the coronary artery, so the blood flow is disturbed. So the SMA stent is fixed at this position. You apply the stress or thermal process, it is expanded, so the blood disturbance is completely cleared, so blood is freely flow in this artery. Next one, the first consumer commercial application was of shape memory coupling or pipings. Example, oil line pipes and water pipes. So you will take it now, this is the small size of the pipe. So this is the coupling material, its radius is bigger. So it is cover these two joining per tube. Then you apply the heat energy or thermal process. So it is tightly bind with the tube. So it is act as the best coupling for these two connecting tubes. So this is the automatic thermal valve. So this is the heat liquid flow in this tube. It is allowed for a certain time. After reach the certain temperature value or the higher value, automatically the SMA spring is compressed, so this valve is closed. So hot liquid is not moving this way. So this is closed. The cold water is moving this way. So this is
removed. This pseudo-elastic property of shape memory alloys makes its way for the usage in indestructible eyeglass frames. Because of these unique properties, shape memory alloys are used in a wide range of applications. The maneuverability of an aircraft depends on the movement of the flaps. The flap movement is controlled by a complex hydraulic system. This complex system can be replaced by using shape memory alloys, which requires only an electric wire to heat up. SMAs are also used in many medical applications. The stent, an equipment used to treat clogged vessels in arteries or veins, can be made of SMA. The stent is inserted into the blood vessel and it expands while heating to remove the clog. SMAs are also used as alternatives for conventional actuators in thermostats, helicopter blades, and hydraulic fittings.
Many commercial applications of one-way SMA. For example, this is a Raychem Corporation product which is known as Cryocon. It is essentially a connector which is used for joining tubes in aerospace applications, and it takes the form of an oval ring of SMAs set at martensite faces low temperature. So initially this is an oval ring. Now when cryocooling is removed, that means from low temperature when you are coming back to high temperature, the ring gets circular and squeezes the tubes and join the two tubes. So it starts from an oval shape, you fit it, and then you remove the cryocooling and it fit the two connectors. So that is cryofit and cryocon system. This is one of the effect of one-way shape memory effect. Now in the two-way shape memory effect, it remembers both the high temperature shape as well as the low temperature shape, okay, which is generally not erased in this particular case. The secret for this is that you need to have a combination of thermal and mechanical cycle training so that it will induce the micro stresses in the material. Then only at the low temperature phase it will be able to go back to the exact shape that you have trained it to have. So then this would result on a preferential formation of twin variants in the martensite phase. So how will be the two-way shape memory effect? This is where you are the original shape at the martensite level. You deform the whole thing and then you heat it up. You are going to get to this particular shape. Now from this shape you cool it, you are going to go back to this particular shape, the bent shape. So now you heat and cool, you will be flipping between these two shapes. One is at a high temperature memory and another is at a low temperature memory shape. Using these, there are many interesting applications that has been developed. For example, the control of aerodynamic surfaces like aircraft wing controls, etc. As you can see here, that SMA wire is controlling these, so-called angle of attack. So that is one application. Microcoils for vibration isolations, or grasping by the robotic fingers, that is also done. Space exploration or rockets, rock splitting. Then development of Nitinol filters or deployment of solar array hinges. There are many applications, particularly space applications of SMA. One such application is how to generate vibration. So what you do here is that, suppose this is a cantilever beam that you have. On that beam you have two sets of SMA wires. Now you actuate one of them, suppose this one, so it gets shortened, so this whole beam gets deformed downwards. And then you cool it and you start to hit the other one, so the whole beam will go to the other side. So then you do these processes again and again, and then you will see that there is a continuous vibration, of course at a low frequency, that's happening by the help of the SMA wire. You can also use these SMA wires for tuned mass dampers, where you have a primary mass and you have the SMA wires and then you have the absorber. The advantage is that for any tuned mass damper we know that there is a spring and a mass that is attached to the system. Now the stiffness of the spring and the mass, these two remains invariant. But in the case of SMA, this K can vary, and as the K varies, so the natural frequency of this secondary system, the square root of K by L, as K varies, then the omega S also varies, and then thus you can actually tune it to different frequencies. One of the fantastic application of SMA is a variable geometry chevron application, which is done by Boeing in Dreamliner aircrafts. If you next time fly in Dreamliner, you will notice that it's the edges near the engine, this is jagged. The reason being of this jagged shape is that initially at this phase, when it is at say detwined or twined martensite, but it is mostly martensite phase, at this phase it has this jagged shape, and this actually helps for vortices to keep the size of the vortices too low, so that it gets attenuated fast. Now as you are heating up, then this shape, and you are going up, then this shape will go back to a flat shape, which will increase the efficiency of the system. So thus you can play between the two shapes and then keep the aircraft really very less noisy. Another example is in terms of amplified SMA actuator. So here this is the SMA in the system, and you apply heat. Now because SMA can give lot of force, so you can deform an egg shaped system. So if you try to deform an egg by the semi-major axis, you will understand what I mean. It is very difficult, you need lot of force. But however, if there is a small deflection here, the deflection is going to definitely get amplified along this direction. That is what actually is done in this particular case as well. One very interesting application of SMA is in the form of SMA wear-based sensor that we have developed. So what you do here is that you take a kind of angle encoder where you have these contacts, and then these are actually conductive things, and these angles are drawn with a known angle. Now these two pins are touching the system, and you are passing the SMA wear-based current. However, the catch is that whenever these two pins are touching this, the SMA wear-based system, only then the current is flowing, and then because of that resistance you are going to get a signal. The moment it is not, or the velocity is changing, you are going to see there is a shift or a phase delay, which you can use in terms of
Merits of shape memory alloys, merits, biocompatibility, diverse field of application. So it is used in the different field, automobile field, medical field, engineering field. So it is used in the different ways. Good mechanical properties, strong and corrosion resistance. Demerits are expensive